We're going to be looking at the circuit diagram right here. We are given that the sinusoidal source is operating at 200 kilorads per second. So this will be our omega. It is going to be equal to 200 times k, with k being 1000. And the coefficient coupling k is adjusted until the peak amplitude of I1 is at maximum. And for the peak amplitude to be at maximum, we know that our resistance or impedance is at 0, because with 0 impedance we'll have the maximum current. So that's important to remember, and it'll come in later in this problem. And then we're also given that our voltage is 560 with an angle of 0 degrees with the same omega. We were asked what is the value of k, and we're going to use reflected impedance, which is what I've included right here from the notes linked below the like button, which includes k, and determine when our Zn is minimum. Again, when Zn is 0, it's the minimum. It'll yield the maximum current. So now that we have all of that information sorted, we are going to use this right here. This is going to be the formula we are going to be looking at, and this is our ZR. Once we find our ZR, we are going to plug it into our Z input. We're setting our Z input equal to the Z for the left side plus the Z, which Z is impedance, of the right side. Then we're going to add this together, and then we're going to do more math with this in a second. So to start this off, I'm going to convert this inductor, and this capacitor to their impedance forms. For an inductor, we're going to have our X of L be equal to our J times the omega times C. Our omega is 200,000 times L. We know that our omega is 200,000, so 200 kilorads. We need to multiply this by, for this part, 1 millihenries, and this will give us a total of 200. We're going to do the same thing for this 4 millihenry inductor, except for this, we're going to get 800. But I forgot the J right here. Don't forget the J, because it becomes an imaginary number here. And for capacitance, it's a little bit different. We're going to have our X of C be equal to a negative J over our omega times C. And this is going to be equal to a negative J times 400. So before we go any further, we're going to calculate the Z1. This is all the impedances for the leftmost side. To do this, we're going to add our resistors. This is going to be 200 plus our J times 200. Now we're going to calculate our Z2. And for our Z2, we're going to have our 100 plus 200 ohm resistors. This is going to be 300 plus our impedances. This will give us a plus J times 400. Now, in the formula that we're given here, we can see that we have this star above our Z22 right here. And the Z22 is basically the 2, and the Z11 is basically a Z1. The star means that it is the reflectance. And to find the reflectance of our Z2, we're going to take our Z2, put a star over it, and then switch the signs basically of this. So we're going to say that this is equal to 300 minus a J times 400. And that's the answer to our reflectance. So we have this part of our formula, however we don't have our M yet. Our M we can find by using this formula. We have that our M is equal to K with the square root of our first inductor times our second inductor. And we can see that if we rewrite this formula right here, we can actually rewrite this as our omega times M divided by our Z22, and then this is in the absolute values, and all of this is being squared. We can factor that squared out, and this is being multiplied by our reflected part. We can plug in the values here, and we can also plug in our omega right here. That way it can match our formula below, and then we can just plug this in. We know that our L1 is going to be the 1 millihenry inductor, so we have 1 times 10 to the negative 3, and that our L2 is going to be the 4 times 10 to the negative 3. And these are both the inductors right here. Now we're going to take this and square root it. After we do this, we are going to get 0.002. We're going to multiply this by our omega. We know our omega is 200 kilos, so we're going to have 200 times 10 cubed, and this is being multiplied by our 0.002, and this will give us that our omega times M is equal to 400K. So this is the next part right here, and now we can just plug everything in. After we plug everything in, we are going to get this equation right here. And remember, this is only for our ZR, so that's what we're solving for now. Now we are going to factor this squared in. So we're going to have a 400 squared up top and then a k squared. And then at the bottom here, before we square it, we're going to have to do something special. Well, we don't want it in this rectangular form, we're going to convert it to the polar form. And to do that, I will just make a side note up here. To convert from rectangular to polar, we're going to have that our Vmax is equal to the square root of our real number, so that's the 300 in this case, plus our imaginary number squared, which is the 400 in this case. And then our angle is going to be equal to the tangent -1 with our imaginary number on top and then our real number on bottom. However, for this specific part, we're not going to be worrying about our angle, we're only worrying about our Vmax. So we're just going to have the square root of 300 squared plus 400 squared, and this is going to give us 500 in here. From here, we're going to rewrite our ZR, and before we do that, we are going to divide our 400 by the 500. Then we're going to square everything inside of here, and then factor it into this 300 minus j times 400 part. So we are going to get this for our ZR, and that's how we would go about for the first part of this problem. Next, we are going to plug it into the green equation that we wrote right here. We have that our Zn is equal to our Zl plus our Zr. So previously, we just found our Zr, and that's all of the work we would have to do to go about it. For our Zl, which is the left impedance, all we're going to do is plug in this Z1 right here. Our Z1 is equivalent to the Zl, however our Z2 is not equivalent to the Zr. We have to do a little extra work, which we did to find it. After we do that, we are going to get this as our Zin equation. I did realize I just made a mistake right here. This should not be 300. Instead, it should be 192. I accidentally put 300 from the problem up here before I multiplied it in. So that's actually the Zr equation. Now back to the Zn. What we want to do is get rid of our imaginary numbers. So I'm going to combine both of them into one formula. So I'm going to combine both of them together and then factor out the j. From here, this will be our new Zn. And now we want to get rid of our imaginary number for both parts. So what we can do is square both of these separate parts and then also put them under the same square root. If we do this, we're not illegally changing the problem at all. And this will be our new equation. From here, I want to again find the part where our z is equal to 0, and our Zn is going to be equal to 0 if we take the derivative of both sides with respect to k. So we have d over dk for both of these sides. And our Zn's a constant, so when we take the derivative of a constant, it's going to give us a 0. So we have 0 is equal to, and now we need to take the derivative of the entire right side. Remember, there's the chain rule that we're going to have to abide by a couple times in this problem. And after we carefully do that, we will get this as our new equation. From here, what I'm going to do is multiply both sides by the denominator. That way the denominator can be cancelled out. And then I'm going to divide everything by 4. That'll get rid of these 2's. And also by a k. That will get rid of that k as well. And then for our 192, I'm going to divide this by 64. That is going to give us a 3. That means I also have to divide this next side by 64. So I'll divide 256 by 64. And this will give us a -4 here. I'm going to rewrite the equation once more for clarity. And this is our new equation. Now I'm going to factor this part in and this part into here. I'm going to combine like terms and then find the value of k. And this will give us the value that our k is equal to approximately 0.35. And that is how we would go about finding the first part. So for part A, we are going to get 0.35. And this is how we would go about doing that. Next, we were asked to find what is the peak amplitude of our I1. Well, our I1 is going to be the Z input, because remember, the Z input is basically the impedance at the beginning terminals A and B. And this is over our VG. So we know, and I'm going to do this in blue down here, that our I1 is equal to the VG, because that's at the start, that's the voltage source, divided by our resistance. It's voltage over resistance, but it's impedance. I use those interchangeably sometimes, and that will give us current. So all we need to do is find the Z input. Well, we have our Z input equation right here that we can use. The only thing that's missing is our K, but we found our K. So now we can plug in 0.35 for each of these K values and rewrite our equation to reflect that. And this will give us this as our answer in rectangular form. Now, if we plug this in here, we can't divide rectangular form by rectangular form. We need it in polar form. So we need to convert this into polar form. And to convert from rectangular to polar form, we wrote out this equation earlier that we can reuse right here. This is going to give us 280 with an angle of approximately 37 degrees. And this is in the correct quadrant because if we graph this, we know that a real number is in this axis and our imaginary number is this axis, so our angle is here. So this is going to be the polar form for our z in. Now we can plug this in underneath our VG, and we know that our VG is given to us right here. We have 560, and this is being divided by the value that we found, which is 280, and then we have the angle of 37 degrees. The angle here is going to be 0 degrees. Well, for the peak amplitude, that's basically the max value, we don't care about current when we're finding the peak. When we look at this, this is going to be basically the max, and this is our angle. And again, it's asking us for the peak, which is equivalent terminology to max. So all we need to do is divide our 560 by 280, and this is going to give us 2. So the answer for part B is 2 amps. And that is how you go about solving for this problem. There's notes for this material as well as a playlist with more problems like this in the description below the like button.